This video focuses on comparison of means tests. Comparison of means tests are used in specific circumstances when you have categorical predictor variables and scaled dependent variables. To understand what I'm going to talk about in this video in an applied setting when you might want to use these kinds of tools, you really need to have already seen previous videos in this series that talk about why I'm using the framework I am and how that framework is put together, how to use the statistical analysis program that I'm using for these videos, how to understand shape, strength, and significance in the somewhat simplified and direct way that I'm using those terms, and you need to have watched some information about central tendency and dispersion, because the central tendency and dispersion discussion in the previous video is now taken out of a univariate context and put into a bivariate context. So the framework that I'm using, to remind you, is just basically about an oversimplified way to choose the correct statistical tool to use in an applied setting, then to think about just what kind of results do I need to be looking for from what that statistical tool reports back to me, and how do I take those results from that tool and how do I write them up, or how do I present them so that there's the maximum chance people will understand what we actually know empirically from the patterns and the data, and how that might answer the original question that motivated us to run the analysis in the first place. So this framework then takes us to comparison of means. Now, before I do the usual pattern where I give an analysis question and I think through why we choose the tool we do and how to use it, let me make some distinctions for comparison of means choices. On the grid, we will note that it just says use comparison of means, but there are two kinds of comparison of means tests, and I'm going to show examples of both. But t-tests, and there are several versions of them, but t-tests normally refers to a particular version called a student's t. The person who developed this tool, rather than name it after themselves, called it student's t, whereas most tools, Kramer's V or Pearson's product moment correlation coefficient, the person who created them puts their own name on it. And the other one is called ANOVA, or an F test, capital F in this case for correct symbol usage, and ANOVA stands for Analysis of Variance. It's an acronym for that. Now, a t-test is commonly used. You'll find them used in lots of places, but it has a particular limitation. The predictor variable has to have only two categories. If you have more than two categories, you can't do a t-test. And a lot of circumstances in regular life don't provide us with predictor variables that only have two categories, and sometimes we might take something complicated like general income level and collapse it into categories of low income and high income, but really we want to be cautious about collapsing it just down into two categories, because that will obscure as much of the variation in the case values as it will help us to clarify the distinction between low and high. So we might want to collapse it into 4 categories or 5 categories, which doesn't make a t-test particularly helpful. Now, the F-test, or ANOVA, is a broadly used statistical approach that's not just in comparison of means, although this is where we usually see it used most commonly. That is, it's used commonly in many tools, but where we see it discussed and we call it ANOVA is in comparison of means. But the F-test, which is at the heart of an analysis of variance, is used in many other techniques, including some we'll look at in later videos in this series. One of the things you need to think about is, if you have, let's say, 2 groups of cases and you want to compare their outcomes on some particular measure. So we want to see if students in classrooms have different grades in their outcome. We're going to look at their grade point average, and we're going to say students in group 1 tend to be students who are involved in extracurricular activities, and students in group 2 are students who are not involved in extracurricular activities. And so I have my 2 groups, and I want to see if they have different GPA in all of their reading, writing, and arithmetic style classes, if you will. Now, when I go to compare them, the question is, when I look at these 2 groups, am I looking at 2 separate groups of cases? And the example I just gave, I am. I have the students who are involved and students who are not involved. And so it's really this group of people in one setting and this group of people in another setting, and the two groups do not have the same students in them. Those are called independent samples. That doesn't mean, if you're familiar with the idea of running a sample, collecting cases from a larger population, and then collecting data from them through some sort of measurement device, that doesn't mean you run separate samples. It means that you basically have two independent groups. So if we have a national survey, which we're going to look at in a moment, and in that survey men were asked questions and women were asked questions, the men and women were all selected in the same sample of the population that was then asked questions. They went out and they said, here's a way to look for a collection of people in the United States who are 18 and older, and we sampled. We didn't ask everybody in the population. We sampled out some people to ask these questions. They didn't run a separate sampling technique for the men and a separate sampling technique for the women, but the men and the women who were in the larger sample are independent of each other. There isn't any sense in which the men in the sample determined which women were in the sample or vice versa. And there's no way that the men in the sample and the women in the sample are the same people. Now, that's an independent samples type test. On the other hand, you might have a circumstance where we say, well, what we want to do is we want to find out if students become involved in some particular extracurricular activity, does it change their GPA? And so we have a group of students and we look at their GPA, and then they get involved in particular kinds of activities, and then at a later time we look at their GPA again and we see if it's changed. Now my group 1 is a collection of students at a particular time, and my group 2 is the same collection of students at a different time. And now the cases in one group are in fact the same cases that are in the other group. In this circumstance, we would use what's called a repeated measure type test. Now, I'm only going to talk about independent sample tests in this video, but you need to be aware that if you're doing anything that involves taking the same cases that are measured at multiple times, then you need to look at a repeated measures kind of test. And finally, I want to make a reference to certain terms that are used with regard to ANOVA. So ANOVA, analysis of variance, is a commonly used term, but then you also will see people talking about a one-way ANOVA or a two-way ANOVA or even a factorial ANOVA. And in fact, there are other phrases as well. Now, ANOVA, just generically, an analysis of variance, is basically talking about how we look at dispersion variance within different groups of cases on particular measures. A one-way ANOVA says that what we're going to do is have one predictor variable, and we're going to see if that one predictor variable is in some sense related to the variance within these groups. So we have a predictor variable, male, female, and we want to see if that in some way is related to variance on the dependent variable. So a one-way ANOVA is saying a one predictor analysis of variance in the dependent variable answers. A two-way ANOVA, not surprisingly then, means that we have two independent variables at the same time that are involved in the analysis. So we say we think that maybe a person's biological sex, male, female, and their race, and we're going to have a simple categorization here of just, let's say, white, black, and other, as clumsy as that classification process is. And then we say now we have white men, and we have black men, and we have other race men, and we have white women, and we have black women, and we have other race women, and we now have 6 groups because we have 3 categories in one of the independent variables, that's race, and 2 categories in the other independent variable, and that's biological sex. And so a two-way ANOVA basically cross-classifies the analysis of variance on the dependent variable within 2 categorizations in the predictor variables. Factorial ANOVA just takes that further and says, now let's basically do it for more independent variables in the analysis. But it also, factorial ANOVA, means that we start taking into account some other things like interaction effects, and we're going to take a brief look at that in this video. The problem is that two-way ANOVA also looks at interaction effects, and factorial ANOVA sometimes is used to refer to two-way ANOVA, So these terms aren't always cleanly and commonly used the same way. I'm just going to refer to anything that's more than a one-way ANOVA, a factorial ANOVA. Like many things I've done in this video series, that's meant to give beginners a practical introduction to using analysis tools in a fixed setting like a workplace. It's going to frustrate people who are professional statisticians. I wouldn't use the terms the same way in interaction with people like myself with the training I've had. But for people who are starting out, this will help you to be able to more effectively grapple with what we're dealing with. Okay. Every tool has assumptions. A shovel has assumptions about what kind of tasks you're going to do with it and when it can be used. A hammer has assumptions about what kind of tasks can be done with it and when it's appropriate to use, right? All tools have assumptions about their appropriate use. This is also true for mathematical tools in statistical analysis. So what we have in most statistical tools is we have a beginning assumption that is built into my framework about the level of measurement that is appropriate for variables to be using particular statistical tools. That's baked into the way I've been presenting every tool I've talked about. I've also, in previous videos, talked about the need to make sure there is no quote-unquote missing data. And what we really mean here is non-valid values. So if, as has been shown in previous videos, we have variables that -1 stands for they were never asked this question in the survey, and so forth, then those numbers, those values in the data set are in fact non-valid. They aren't numbers that represent measurement on what the variable is supposed to measure. And so we want to make them go missing in the analysis. And so by custom, we commonly call all of them missing data, even though you might initially just intuitively think, well, missing means we don't have a value at all for a case. What it means is we have non-valid values or no value. And so we want to identify and make sure that any non-valid values are removed from analysis before we do anything with any particular tool. We also have talked before about not having serious outliers. This doesn't affect every statistical tool, but it does affect some. So in the last video on central tendency and dispersion, there was a comment or two made about how serious outliers will distort the mean and distort the standard deviation. And if you have a set of or a serious outlier, then you have to think about whether it's distorting those particular tools. Whereas a median couldn't care less about serious outliers. But it's always something that we look for. In comparison of means tests, then since we are going to compare means, and we are using the arithmetic mean here, then we know it's distorted very much by outliers, and in this circumstance we have to make sure that there are no serious outliers that would be distorting the values of means or standard deviations, since means and standard deviations, as we'll see, are deeply involved in what we do in comparison of means analyses. Something else that we're going to talk about more in coming videos, particularly correlation and regression, is the assumption of linearity. When we say that a predictor variable and a outcome variable, an independent and a dependent, if you will, when we say they're related in a linear way, it's the same basic idea of direction of effect that was talked about in shape, strength, and significance. That we can talk about as you have more of one, you have more of the other, or as you have more of one, you have less of the other. The assumption there is that there is some sort of straight line relationship. Now, most of life in the social reality isn't straight line. It's kind of messy and it's kind of murky. But we generally find that using a mathematical straight line tends to see a lot of patterns in a lot of kinds of data relationships. And so a lot of tools use linearity as an assumption. So in this particular tool, and when we talk about correlation and regression later, there will be some discussion about linearity. Linearity is not an assumption of comparison of means tests. You can still consider if there is a linear relationship if you want to look for one. You can look for direction of effect if you have both variables ordinal or higher. The dependent and the independent are both ordinal or higher levels of measurement. You can do that, but you don't have to have linearity to be able to use these tools that we're talking about in this video. Now, I didn't make a point of it in the cross-tabulations video, but what we looked at there in terms of the measures of association and so forth are called non-parametric statistics. And I didn't talk about it because the time it becomes more important is when we actually have parametric statistics. Remember that a parameter is a descriptive number for a population of cases, and a statistic is a descriptive number in some form or other for a sample of cases. So when we say that a tool is parametric, it means that we assume something is true, that some parameter is true for the population. And the two parametric assumptions that commonly creep into a lot of statistical tools, it's true here, it'll be true in correlation, it'll be true in regression, are two issues. One is normality, and that is to say that we assume that there is a normal distribution of the dependent variable, a normal distribution in the circumstance we're going to talk about here even, within each category of the predictor variable. And we assume that there are equal variances, equal, if you will, equal dispersion. And that's also called homoscedasticity if you like to use fancy terms to impress your friends and neighbors. So the question here is, with the parametric assumptions being in place for comparison of means tests, and so now we have men being compared to women, and we're going to compare the mean and standard deviation for men on some dependent variable to the mean and standard deviation on women for some same dependent variable. Then we say, do we really need there to be a normal distribution in the men's values on the dependent variable and a normal distribution in the women's values on the dependent variable? Do we need there to be equal variance, equal dispersion amongst the men's values, equal dispersion, equal variances in the women's values? Well, honestly, most folks doing statistics tend to skate pretty close to or over the line with assumptions of normality, because most data isn't normally distributed when you're talking about data about people, about socially constructed units like countries or states or counties or cities. If you're talking about physical sciences, normality is not all that unusual. You have normal distributions amongst number of petals on flowers and normal distributions and a whole bunch of things that happen in physical reality, but not so much in social reality. And so we would use a term robust, and we would say, is the statistical tool able to function fairly well even if we're not sure we've met the assumption of normality? That is to say, is the statistical tool robust enough to handle this violation of an assumption? And to be frank, we play pretty fast and loose with this in general practice, even though we should be pretty cautious about it. But those of us who do this for a living, we're aware of this assumption, and we're cautious about overclaiming when we know that we have non-normal results. There are ways there are ways in JASP, there are ways in other stats programs to actually test to see if these assumptions are true. And some folks use them and some folks don't. In a practical setting, you just need to be aware of these things, and if you want to explore this further, it's beyond the scope of this particular series of videos, but be aware that there is an assumption of normality, and it might be something you should look into. Equal variances gets looked at more, but even equal variances oftentimes doesn't get a lot of attention in practical work. The real point here is, if you think there's much chance that homoscedasticity or normality are violated, then you need to be cautious to not overclaim from the results. You need to probably say, we think that we have data that suggests possible patterns, but we're not sure we fully meet the assumptions of the mathematical tools, and so we have to be cautious about taking this as too firm and fixed. it might be your safest way to move forward. Okay, so as I've done in previous videos, let me just say, what are the basic statistical tools you would use if you're doing a particular kind of approach? Well, if you're doing a t-test, and we're going to run some t-tests in a moment here, but only one really, because t-tests are so limited because of that need for a two-category dichotomous predictor variable. You're going to look at the shape by looking at the means and standard deviations within categories of the independent variable. So if we're comparing men to women, and we're looking at their GPAs or whatever, then when we look at the men's GPA, we'll look at the mean and standard deviation for GPA for men, and we'll compare that to the mean and the standard deviation for women. So we're looking at the means and standard deviations within the categories of the independent variable. This sounds a lot like crosstabs, except that crosstabs, we had to look at a distribution of percentages within the categories of the independent variables, and so we had a lot more numbers. Frankly, comparison of means is easier to read. The results are easier to work with because you don't have so many murky percentages to try to figure out what pattern you think you're seeing. For strength, there isn't really, I don't believe, there's a good tool for strength for comparison of means tests doing a t-test. I'm going to say with an f-test you should use eta squared, and I would even say if you're doing a t-test you should probably look at eta squared instead of Cohen's d, but Cohen's d is commonly used. Now, my concern about Cohen's d is based on things I'm not going to unpack here, but fundamentally all Cohen's d does is it says you have the two means for, let's say, the men and the women, and you want to see how far apart they are. The null hypothesis, remember, always says there's nothing going on here. There's no relationship between the two variables. So if the null hypothesis is true, the men and women will have basically the same mean value on whatever the dependent variable. It doesn't matter if that mean value is high or low. It means that they'll be the same for the men and the women, or nearly the same. So what Cohen's d does is it says, are the means different? Because that's not what the null predicts. And so we say if we take the mean of one group and we subtract away the mean of another group and see how far apart they are, how close to zero is it? And then they turn that into a standard deviation. So in terms of, instead of just saying it's this many units apart and that's that many units above zero, it then turns it into standard deviations. What you're really seeing is how far away is this result from what the null predicted. And there's value in that. It does, in fact, do what strength or effect size measures do. It allows you to make a prediction, because if they're more different than what the null says, then having that independent variable will help you to make predictions. But the problem with Cohen's d is that it's kind of hard to figure out exactly where to draw some lines. If you've watched the shape, strength, and significance video, then you'll recall that I talked about two basic kinds of measures of association or correlation. One kind tends to give you a number between 0 and 1, and you tend to use some rules of thumb if you're a beginner at figuring out exactly where the lines are for a small or a moderate or a large relationship. And I use, though everybody kind of disagrees on exactly where the lines are, I used the values of 0.2 for a weak relationship and 0.3 and 0.5 for moderate and strong. And then I said there are other measures of association that basically look at the proportion of the variation explained, and we'll look at one of those more in this video. Now, Cohen's d isn't quite either of those. It doesn't quite work like the measures of association and correlation, and because it's not one of those. And it doesn't quite work like the measures that tell us the proportion of variation explained. So Cohen's d runs on its own scale, and you're going to basically have to decide what you want to do. People might use numbers more like 0.2 or 0.1 is weak. They might use numbers like 0.4 is moderate and 0.6 is strong. But Cohen's d ranges way above 1, potentially, right? If you have two means. You have a mean GPA of 3.4 for one group, and you have a mean GPA of 2.2 for another group. Then you have a difference there of 1.2. And Cohen's d will take 1.2, and then it'll turn it, depending on the standard deviation, into some other number. But you can have Cohen's d values that are harder to figure out exactly where the upper limit is. There's no clear upper limit to this. There is no certain upper limit to what the number can be, and it makes it a little harder to read. Nonetheless, Cohen's d is commonly used, and if you kind of want to go with that, maybe 0.1, 0.4, 0.6, something like that. But, you know, you work with it as best you can. There are a lot of other resources on the web that can help you to think about where you would want to draw your line. Just don't overclaim when you find your results. Don't say that you've got a strong, big effect going on here if you've got a small Cohen's d. If you've got a really small Cohen's d, don't start claiming, you know, that something's happening when it's not, just because of statistical significance. All right, statistical significance. The t-test is, in fact, a statistical significance test. That's what it's built to do. And it basically uses a distribution of the t-statistic to find out how far away from what the null predicted your sample data are. And so you look at that p-value, the probability value that goes with the t-test. And I talked about statistical significance and p-values in that shape strength significance video. So, comparison of means. You're going to use a t-test. You're going to compare means and standard deviations within categories of the independent variable. You're going to probably use Cohen's d because it's commonly used. There are a few others, Hedges g and such, but they're basically the same thing as Cohen's d. And then you're going to get the significance from a p-value, like we always do. This p-value will be the one that comes from the t-test specifically. If you do an f-test, or an ANOVA, analysis of variance, again, you're going to compare the means and standard deviations within the categories of the independent variable to figure out what's really happening. Do men have more of this, or do women? Are they the same? Seeing the shape or the direction of effect or any of those things are going to come from comparing the means and standard deviations. Strength is going to be done using a tool called eta squared, which literally measures using squared deviations. Using a mathematical approach, eta squared basically finds out what proportion of the variation in the dependent variable we can now predict better because we know independent variable categories for the cases. So if we're comparing men and women, if we tried to guess people's GPAs, and we would get a lot of them wrong, even if we knew the mean and we knew the standard deviation, we'd make a lot of error guessing each student's GPA. If knowing they're male or female, if that helps us using the mean for men and the mean for women to get closer guesses and make less error, that's what eta squared literally tells us about. It tells us the proportion of the variation we now can explain because we know the independent values for the cases. And then we now use a p-value from an f-test, which we'll see in the examples that we do. So let's pick an analysis question. In the last video, I talked about how many hours a day do people watch television, and now I'm going to add the question, do men and women watch different amounts of television? We're going to use the 2018 General Social Survey data as we have been, and the dependent variable will still be that TV hours measure that we were using in the central tendency and dispersion video. So we answered the first question here. We answered it with the central tendency and dispersion video, and the second question here that we're going to focus on is the one that needs something else. Let's figure out what else we need. Here's the variable itself. We saw this in the last video as well, but you'll recall that basically people were asked on the average day about how many hours of television do you watch, and they could answer anywhere from 0 to 24, and then a value of 98 meant they don't know, 99 meant they said they aren't going to answer, and a -1 means they were never asked this question. So that's our dependent variable. And when we go to look at this, we say, do men and women watch different amounts of television? Then we first look to see, are we doing a one variable, two variable, or simple multivariate analysis? Well, I am not saying, tell me the patterns from how many men and women were in the population or the sample. Then tell me separately the patterns for how many hours of television they watch. I'm saying, does the pattern in biological sex, being male or female? Does it relate to the number of hours watching television? So I am in fact doing a two-variable analysis. So any tool I choose is going to be in this row of the choosing grid. The dependent variable is number of hours watching television, which does have an order, and in fact does measure with a standard unit and does have a value of 0, so it's a ratio level variable, and so we're going to be in that column. Now when I put in the options for scaled variable analyses, scaled dependent variable analyses, I run into a problem here because when I get down to two variable analyses, it says, what's your independent variables level of measurement? If it's interval or ratio, then we're going to have one column we're going to look at. If it's nominal or ordinal, we're going to have another column. Well, it turns out that we're using male-female, so it is nominal or ordinal, and so we're going to choose something in that column, and there we go. When we grid that out, we get comparison of means, and so we say that's what we need to do. We need to do a comparison of means test when we have basically a categorical predictor variable in a two-variable analysis, and we have a scaled dependent variable. Okay, that sounds like our circumstance. We're talking about male-female, and does that help us to predict number of hours watching television? Okay, so what do we need from the results? Well, anytime we have two-variable analyses, we need shape, and we need strength, and we need significance, and we've already listed what tools we specifically would use statistically to be able to do this, so we're ready to run to an analysis. Okay. So I'm going to jump over to the JASP program, and we're going to go to this 2018 General Social Survey. What I want to do, let's make this full size. Now, I need to go in first. I always need to go in first, and I need to see what my preferences are for missing data. All right, so, I don't have I need to have 98, which was, I don't know how many hours of television I watch. I need to have 99, which was, I'm not going to tell you how many hours of television I watch. And I need to have -1, which is going to say I don't actually, I was never actually asked this question. Okay, so that gets rid of our missing non-valid categories. So we're going to go up here and we're going to go to t-tests, and now we have independent samples t-test, and that says that the groups that are being compared, the categories of the independent variable, the grouping variable it is sometimes called, that the cases in the different groups are not in any way related to each other. Their inclusion in the groups is independent. And we have paired samples, which is a repeated measures. It is a circumstance where the samples are paired. The cases in one group determines the cases in the other group. For example, if I measured a collection of people at time 1 and then measured the same people at time 2, then it's the same cases. Which cases were in group 2 are in fact determined by which cases were in group 1. Okay, and then there's also something called a one-sample t-test that allows you to simply compare for a set of cases whether their results compare statistically differently, significantly, inferential statistics from an assumption of 0 for the mean. That's not used very often. All right, so we're going to do an independent samples t-test, and we're going to go and we're going to find this TV hours measure. All right, we're going to put the TV hours independent measure over there in the variable list, and then you notice we have a grouping variable, and because we're doing a t-test, we're going to have to do something that only has a 2-category predictor, and so I'm going to come down here to sex and put it in as the grouping variable, and it gives me immediately the t-value, which is a particular tool that sees how far apart the means are, and there's more to the formula, but it basically says how far apart are mean 1 and mean 2 from group 1 and group 2, and then it says how far away is that from what the null predicted, which is that they would be the same, and so the difference would be 0, and then it basically gives me the probability that we could get this t value for the men and women if in fact if in fact the null were true in the population that this sample was drawn for. And we see that the p-value is 0.198. Now, that's fine. We already know from the previous work we've done that if this number is less than 0.05, we're going to say it's statistically significant. We're going to reject the null claim. This number is not less than 0.05, and so we're going to say it's not statistically significant, and we're not going to reject the null. But what's happening? Just knowing the statistical significance doesn't really answer any practical question. I need to know what the actual mean hours of television watching are for men and for women before I can make any meaningful decision about what this tells me. So I need to go over here and I need to add what are commonly in statistics program called the descriptives, even though lots of tools describe the patterns and describe the cases. It's commonly used for referring specifically to means, well, central tendency and dispersion. And so now I can see that for the men, the average was 2.8, and the average for women was 2.9, and the average spread around that mean for men was 2.4 hours of television watching, and for women it was 2.8. All right, and then I say, but what about the effect size? And I'm going to, as I said before, use Cohen's d, and so Cohen's d comes out to a negative 0.066. Now, Cohen's d can be negative or positive, just depending on which mean is subtracted from which mean. The negative and positive don't actually tell you anything necessarily. Don't assume it's a direction of effect. In some tools we use, and some we're going to use, a negative or positive sign tells you a direction of effect, but since especially we have a nominal variable here, as we've said before, if you have a nominal variable, you can't talk about direction of effect. Okay, looks like we have all the pieces we need here. Let's go ahead and add the ANOVA analysis. So again, I can do the kind of independent samples, ANOVA. I can do the repeated measures, ANOVA. And then there are analysis of covariance and multivariate analysis of variance, which is it basically builds around the idea you could have multiple dependent variables and do some modeling. So we're just going to use ANOVA, and we're again going to get the dependent variable. And we're going to put the dependent variable in as our dependent variable. And now you notice that there are some other options here. Because I can have more than one, independent variable with ANOVA, with an F-test, and I can have multi-categorical ones. All right, so what I want to do is I want to go ahead and just use sex for this example, even though I could do this with a t-test as well. And you see there are lots of choices now. This is a very able tool. Statistically, it can do a lot of things. We can build things called models. We can check those assumptions. This was also true if we go back up to the independent samples t-test, right? There are ways to check for normality and equality of variance, right? But if we go into ANOVA, we can also check for those things, again, beyond the scope of what I'm going to do here. But if you wanted to explore further, you could learn how to do some of that and how to interpret it. We can do a whole bunch of things. Post hoc tests are something that if you ever end up using a lot of ANOVA work, you really should learn more about post hoc tests down the road as well. What I want to do is I want to go to additional options, and I want to get the descriptive statistics so that, again, I can see the means and standard deviations, see just what the shape of the pattern is. And then I also want to look for an effect of an estimate of the effect size. And in this case, I'm using eta squared, which is a Greek lowercase eta, looks kind of like a funky long-tailed n. Okay. And so I have these results. Let me also point out that there's something else I could have done here. You may recall from the video on central tendency and dispersion that we have a very skewed distribution of TV hours, of the number of hours people watch. There were even, I think it was 4 people who say that they watch television 24 hours a day on the average day, which sounds kind of odd. Apparently, they're watching TV while they sleep or something. So we might say, well, you know, I just want to point this out to you that you can do this. We can go into the filter option, right? And we could go down here and we could find that TV hours variable, which was 273. This scrolls quite a bit slower than the other interface does for the analysis choice. and we put the 273. We just click on it, and 273 is dropped in here. And then I say, well, I want to filter for cases that have, on that variable, have less than the value of, let's say, 20 hours. So I'm only going to include cases that have up to 19 hours of television watching. All right, so I say, okay, that sounds good. And I've set that now as a case filter. There are unaccepted. Wait a minute, save. And then I'm going to go back over to look at the analysis, and I can see the difference here. Now, if I thought that those cases were outliers that were distorting the values greatly, I would rerun it like I've done here, and I would look at the results and see how different they are from when I included those potentially outlier cases that might be distorting things. All right, so that's the basic idea of what we're doing here. Let's jump back over and look at these results in a larger format. So here are the t-test results that we saw, and we're going to try to describe the pattern in words, provide statistical evidence so that people can decide if they agree with us in how we've described things in words. We described it in words because most human beings answer questions, understand meaning in words, not in numbers, and so they want us to describe the pattern in words. We want to make sure they understand what cases are involved. These are this is a sample of adults in the United States gathered in 2017 and 2018, and we want to be sure that they understand exactly what was measured so there's no misunderstanding of what this might or might not tell us. And we also, when we're describing these things in words, want to make sure that when we start speculating about what it might all mean or why it might all turn out this way, that we keep those interpretations separate so we can keep our description of empirical patterns separate from our discussion of what we think it might all mean or what we might tell us or what we might do or the consequences of it. So we keep our interpretations separate in our writing and in our presentation enough that people don't think we're trying to mislead them and claiming our interpretations are factual, when in fact they are extrapolations from what is factual. All right, so here we have the t-test results, and we can see that the mean value for men was 2.8 hours on average watching television, and for women it was 3 hours on average watching television. Okay, and we can see that for men on average were varied around the mean by about 2.6 hours, and women on average varied around the mean about 3 hours. All right, so what would I say in words? I'd say that basically they're the same. Women on average watch a tiny bit more television and maybe have a tiny bit more dispersion around the mean. They have more varied answers, but really 2.8 hours, 3 hours, men and women basically watch television on an average day about the same amount. Okay, well, my Cohen's d agrees with that. It's near zero, and if it's near zero, then basically there's no effect size going on. There's no difference here. So you look for trend, and you look in the shape to see trend and variation, and the more trend there is and the less variation there is, then the more that you'll have greater strength of effect, and the more strength of effect you have, the more likely you are to be able to reject the null. Well, we don't have much strength of effect, so we don't reject the null. We actually have a p equal to 0.269. So there's a 0.269 probability. So it's basically 1 in 4 chance that we could get these results with the null hypothesis being true in the population. All right, so men and women basically watch about the same hours of television. Now, I also said, let's put in that with TV hours less than 20 case filter, and here are the results that we got for that. And so we can basically see that now the mean is 2.8 and 3.0, 2.8 and 3.0 if I round, 2.8 and 3.0 if I round. So really, the means aren't changed much by removing those potential outliers at all. The standard deviations were 2.6 and 3.0. Now they're 2.4 and 2.8. These aren't big changes. Those cases aren't causing major distortion in anything. So we're not very surprised that the Cohen's d is basically the same, 0.07 compared to 0.06. In both of those, there's no effect going on here. There's no effect size. And in both circumstances, we have p-values that say we cannot reject the null. We fail to reject the null in this circumstance. All right, The ANOVA results, of course, show the same basic thing because it's the same data. What you find is, of course, we have exactly the same means and standard deviations. Now, I left the outlying cases in, you recall, when I was doing this analysis. And so I would still end up describing this as saying men and women basically have the same results here. They watch TV about the same amount, and they have about the same amount of dispersion around the average. And I come to a eta squared. Now, eta squared, this is our first time looking at eta squared. Eta squared is the proportion of variation explained by the predictor variable. So you can take a proportion, which runs from 0 to 1, and you can turn it into a percent by multiplying by 100. So I could actually multiply that number by 100 and talk about the percent of variation explained by the predictor variable. Or to make it more straightforward, multiplying by 100 just means you move the decimal place 2 places to the right. So instead of 0.001, I have 0.1. Biological sex helps us predict 0.1%, 1/10 of 1 percentage point more of the variation in TV watching than we could predict without knowing gender. That would be nothing. So we really gained nothing in percentage of variation explained by knowing if they were male or female. And the p-value, again, demonstrates that the number is much greater than 0.05, and we need a number less than 0.05 before we're going to reject the null and say, well, we don't think the null could be true for the population of cases this sample represents. So again, same findings, of course, because it's the same data. But the benefit of the ANOVA is that I can go on to do analyses that involve multi-categorical predictor variables. All right. Let's do another analysis question. Let's move to countries as our cases so that we move to a context where the cases are not as intuitively obvious to us. I've tried to use individuals as the examples oftentimes in the examples in these videos because most of us think in terms of individuals and their behaviors and their beliefs and so forth. But I want to compare some countries because oftentimes you may find yourself in a regular setting having to compare different agencies, different counties, different states, different countries. You may find yourself having to compare cases that aren't just individuals. So in the video that looked at central tendency and dispersion, we asked if countries in different regions had different percents of the population saying several different things were never justifiable, one of those being prostitution. Well, I'm going to go forward with the one about prostitution and say, do countries in different regions have a different percent of the population saying prostitution is never justifiable? Again, this is a world data set that I've put together. The data comes from a variety of years. Some of the World Health Organization data I dropped in comes from the early 2000s. Most of the rest of the data comes from 2010 to 2018 or so. We have data about economic well-being or economic performance of the countries. We have data about population health characteristics. We have data in this data set about political and civil liberties. We have data in here from population surveys, samples of the population that were surveyed to find out their views on a variety of different things. So we have a whole bunch of stuff here. Now, we're going to use that same dependent variable that basically said for each country, what percent of the population in the sample, what percent of the sample, basically said that prostitution is never justifiable. Now, our independent variable is region. And I just want to take advantage of this moment to say you should always think whenever you're doing any analysis about the variables being involved and think, do I think this variable is well constructed? Because if it's not, running analysis is probably not a great idea. Here you have a color-coded map that shows the different regions according to the World Health Organization. Now, I didn't choose the World Health Organization regions because I had some particular affinity to them. I just picked a region variable. And I like this one as an example because it has some interesting decisions that get you thinking about why would I construct regions this way. So for example, it only has a few regions, right? It only has 1, 2, 3, 4, 5, 6 colors on the map. It only has 6 regions that all countries are put into. Maybe we should have had more. Maybe Canada and the United States, for whatever reasons you might think, oh, they're a region, should be separate from Mexico, the countries in Central America, the countries in South America, because you might say, well, there are more countries that are focused on a different cultural background. Although then you'd have trouble putting Brazil in there because it has more Portuguese background rather than Spanish. Right? How do you decide which countries go? Maybe you're going to say, well, I'm just going to go by continents, and you're going to just use physical geography. But as well, why would you choose that as your region variable? If we think region affects cultural views of prostitution, whether it's justifiable or not, then we need to think about why we built the regions the way we did. All right, so let me point out a couple of things about this region variable. It's not unusual to do most of what's done here. For example, you'll notice that we have what they call the Eastern Mediterranean countries, what many times is called the Middle East and Northern Africa. Those are oftentimes put together because those are the countries that have a substantial proportion of the population that are Islamic. And oftentimes that includes across the top of Africa, and then all of Africa below the Sahara Desert, thus sub-Saharan Africa, is normally put in a separate category. Europe could have been put into a number of different distinctions here. I mean, do we really think that Southern Europe, Portugal, Spain, Italy, Greece, that they are similar to Northern Europe, Scandinavian countries, right? So Norway, Sweden, Finland, so forth. Do we think that Western Europe, for example, France and Germany and the UK, are similar and should be categorized together with Eastern Europe, Ukraine, Russia, Croatia, and so forth? This is Europe, as it's commonly done. What about Asia? This is someplace where they've done something a little different than what is commonly done, and it gets you thinking. So we have South Asia. So we have India, we have Pakistan, we have Bangladesh, we have Myanmar. We have countries over here, and then we have East Asia. But interestingly, they've called this Southeast Asia, and they've put some countries that are, this is normally what's called Southeast Asia, and they've put some countries in Southeast Asia with South Asia, and then they've taken others like Vietnam, and they've put them over with what they're calling the Western Pacific countries. And in a very interesting distinction here, they're going to put countries like China in the same region as they put Australia. All right, that's fine. They have reasons for doing this that are probably related to world health issues, because it's the World Health Organization, which is a branch of the United Nations larger structure, that basically determined how this region was constructed. Okay, I don't care. You need to think, though, about which variables you're using. And since we're going to use region as a predictor variable here, it was a good chance to illustrate that you need to think about exactly what variables are involved so you can think about what you can claim out of the statistical results that you get. The World Values Survey, where they asked the population, do you think that prostitution is justifiable? The dark green countries and the blue countries all have participating data, but you'll notice that there's a lot of that kind of brown orange kind of country that they don't have data for, a lot of countries that they don't have data for, and that there are light green countries, and many of those there's no data for in this data set either. So you'd have to say, now, what am I talking about? I'm not talking about sub-Saharan Africa very much, because most of sub-Saharan Africa, I don't have data for them. So you'd have to be aware, stay true to the cases when you talk about these results. Okay, so let's jump over and let's look at the world data set. And now, using the world data set that I've put together here, let's check what we have for missing data, like we always should. Make sure that whatever we have, now I no longer need that missing, I no longer need that missing, I no longer need that missing. In this data set, actually, the way it's set up, if there are no non-valid values for any of the cases in any of the variables. All right, so cleared that up. Now what I want to do is I want to go to ANOVA. Remember that I now have a predictor variable that has a variety of regions, I believe it's 6, that isn't going to work for a t-test then. It won't let me choose that variable for a t-test. It's not a repeated measures ANOVA. Which countries are in which region is independent. So I go to ANOVA. I'm going to find my variable that talks about whether the percent of the population that believes that prostitution is justifiable. All right, and it was asked, this data from the World Value Survey that's publicly available looked at earlier years. There are many waves that have happened since then, but the data isn't as easily accessible. They hold on to it and do their results and reporting before they make it available to everybody to use. So we've got the wave 4, which was sometime in the late 2000s, as I recall, and that's going to be my dependent variable, and that's the variable that asks if prostitution is ever justifiable. What percent of the population say it's never justifiable? And then I'm going to look for that region variable. It happens to be up at the top here. It's the World Health Organization region is the one I'm using here. And again, I'm going to jump into this additional options because simply knowing I have a statistically significant result. That's great. I don't know what it is, but it's apparently we can reject the null that all of the regions have the same mean value on percent of the population that says prostitution is justifiable, is never justifiable. Okay, so we need to find out what the means and standard deviations are, and we need to have some effect size measure. Now, that's the results that we can make some sense of. Let's jump back over where we can look at this in a larger format. All right, so here's what we do. I've moved the descriptives up to the top here because that's actually what we're more interested in. And you can see that in Africa, 80% of the population, on average for African countries, we're talking about countries. Region is a variable, and people were surveyed, but the cases in the analysis are countries, and you have to stay true to the cases. Everything I talk about here, everything you would report here, you have to make sure your audience understands the cases were countries. So looking at the percent of the population that says prostitution is never justifiable, for African countries, the mean was 80% of the population. So we have 5 countries, and they all had different values of percent that said prostitution is never justifiable. On average, for those 5 countries, we had 80% of the people saying prostitution is never justifiable. In the Americas, it's 60% is the mean. In Eastern Mediterranean region, it rounds to 94%. In the Europe region, which has 20 different cases, 20 different countries, a lot of data collected from countries in Europe, it has a mean of 55% of the population, 55% of the sample that was surveyed, saying that prostitution is never justified. For the Southeast Asia, which remember was India and the countries just to the east of that, 87, 88% if you round. And for that Western Pacific region, it was 67% as the average for those 6 countries. Now, we also can note that that Western Pacific region has a great deal of variation, right? 20 percentage points. On average, countries varied 20 percentage points from the mean of 67. So these 6 countries have a real wide variety of views. Meanwhile, in the Eastern Mediterranean, or the Islamic countries, there's very little variation amongst the values from the countries. For those 5 countries, all of the numbers, all of the percent of the population who say prostitution is never justifiable, they're very close. They only vary away from the 94% mean by about 4 percentage points. So there's a lot of agreement amongst the countries in those regions. So what do I conclude? I could basically compare and contrast because I have a nominal independent variable. I can't talk about a direction of effect. I can't say as you have more region, you will have these different values, this higher or lower likelihood of a value on the dependent variable. I would simply have to say which regions the countries have higher and lower values. Now, notice I kept talking about the Eastern Mediterranean countries being the Islamic countries, and that is why they're put there. But you know, all we know is that those countries are in a region together. We don't actually know if it's Islamic people who are making this distinction, right? We don't actually know anything about the individuals making a choice. We know that there are certain patterns of religious affiliation in the countries, and I'm implying that we should be dragging that into this analysis. I am basically putting my interpretation into the midst of my discussion, violating my own rule. And you see how easy it is. All right, so In terms of effect size, wow. If I wanted to explain the answers that countries have, the percentage of the population that says that prostitution is never justifiable, I can explain 49.7% of the variation knowing the region they're in. That's an incredible increase in my ability to predict the likely values for countries. So that's a very, very strong relationship. Region has a very strong predictive utility with the predicting the percentage of the population in a country that says prostitution is never justifiable. This is statistically significant. P is less than 0.05. We do reject the null claim that the means for all the categories will be the same. So the shape is pretty clear. Big differences. We know they're big, big differences because we have an effect size measure that sees how there's a trend that, and by trend here, when we're doing bivariate analysis, we're saying if there's a lot of variation in the percentage of the population saying these things, and the means are all the same for the countries, then there's variation, but there's no trend in how the predictor variable is related to that. But there is a trend in how this predictor variable is related. There is a lot of effect going on here, and eta squared shows that. And because there's a lot of trend, because there's a lot of strength of predictive utility, we do end up rejecting the null hypothesis. I've put this into a line graph so that you can see one way that you might report this. Now, I've sorted them. Let me jump back. These results, the means are actually listed over here by region alphabetically. AF, AM, EM, EU, SE, WP. So these are just listed alphabetically. All right. Now, what happens here is that I have sorted them when I created the line graph in Excel. I sorted them so that they go from the smallest number to the highest number in the means. And now you can kind of see the difference. But be careful. That doesn't mean I can talk about a direction of effect, even though as I move to the right on this chart, I do have higher means on the dependent variable. There is no moving to the right or left on this chart because the categories of the independent variable are nominal. There is no order to them. I could easily put these in any order. So be cautious about reading a direction of effect into this. And yet it might be helpful to an audience to see from those countries that tend to have a lower percent saying it's never justifiable to those countries that say there's a higher percent saying it's never justified. It might be useful to put them in this order, but be cautious to not misunderstand what it shows us. Now, I'd also talked in the last video about box plots or box and whisker diagrams, and so I made one. Now, I sorted it a little bit differently in the raw data, and so they ended up in this order. But you can see now that for Europe, you can see what the median is, and the mean is the x, and the mean and the median for the Western Pacific. And look at the amount of variation amongst these countries in the Western Pacific region, right? Whereas there's hardly any variation at all over here in the Eastern Mediterranean region amongst the countries' values on percent of the population saying that prostitution is never justifiable. If your audience can understand a box plot, this shows a lot more information. But if your audience can't understand a box plot, maybe a line chart. But again, the line chart could be misinterpreted. We also could have done a bar chart. You can see how this line graph, you could have a bar for each category of the independent variable that goes up to this height. This line chart is basically the same as a bar chart, except it uses a line to connect the means instead of showing bars. It's technically easy to misunderstand what this is showing you, but it's much more intuitive to the average population that doesn't know how to interpret these kinds of box plots. Okay, so comparison of means. Comparison of means is useful when you have a categorical predictor variable and you have a scaled dependent variable. We're going to need to move on now and talk about what do you do for a simple multivariate version of, or a two-way ANOVA, what I'm going to lump into factorial ANOVA. We'll do that in the next video.